reduction. Okay, so how to reduce this post correspondence problem as undecidable. Okay, so reduction, you can take any known standard problem. Okay, it is not like whatever I do only you have to do. If you you can take any known standard undecidable problem. You have to choose any known standard undecidable problem and you have to reduce it to your problem. Okay, in our case PCP is our problem, post correspondence problem. I'm going to reduce going to take a standard undecidable problem. I'm going to reduce it to a post correspondence problem. If I'm able to do that, I'll be able to prove that post correspondence problem is also undecidable. Okay, I repeat, my aim is I'm going to prove post correspondence problem is undecidable. How do I prove that? How do I do that? I'm going to take any once known standard undecidable problem. If I'm able to reduce that standard problem to PCP, a post correspondence problem, then I can say that PCP is also undecidable because I know that that standard problem is undecidable. Okay, so that's a concept. Generally, they take the problems like universal language. There is a problem called universal language. And there is another problem called membership. Given a word, I cannot tell if it is a member of a grammar, membership of grammar. Given a word, I can telling that if the grammar generates the word again is undecidable. And again, Turing machine acceptance. Turing machine acceptance is again a flavor of halting problem. Turing machine halts with the accepted state. Okay, this is a very known standard undecidable problem. Okay, so these are standard undecidable problems. Universal language problem, membership of grammar. So given a grammar, given a word, you'll have to tell if this word can be generated by the grammar. And Turing machine acceptance is you're going to say that Turing machine halts in an accepted state. Given a Turing machine, given a word, you have to have a deterministic algorithm that tells you, saying that, okay, for any word, for any Turing machine, your algorithm should be able to say that, okay, this Turing machine halts in an accepting state. So will you be able to write a generic algorithm like this? No, because halting problem is undecidable. This is also undecidable. So since we know Turing machines, we are choosing this to prove that. I'll take Turing machine acceptance as a standard undecidable problem that I know. Then from that, I'll try to reduce it to a post correspondence problem with an example. If I'm able to reduce that Turing machine acceptance to a post correspondence problem, then I can 100% say that PCP is also undecidable. Okay, so now what I'm going to prove is, I'm going to prove is if I'm able to reduce reduction, I'm going to prove if I'm able to reduce a Turing machine acceptance problem to a post correspondence problem. I'm able to create dominoes out of this Turing machine, and by arranging the dominoes, I'm able to for a string that is accepted by the Turing machine, and I'm able to make an arrangement out of the dominoes that I created. If yes, means the Turing machine acceptance is being reduced to the post correspondence problem, and I can say that PCP is also undecidable. Okay, so let us take an example Turing machine. So what we are going to do, we are going to take Turing machine acceptance, which is a standard known undecidable problem, and we are going to reduce this to reduce Turing machine acceptance to a post correspondence problem. Okay, so if you do that, this is undecidable. So this also becomes undecidable. So let us take an example Turing machine, a standard example Turing machine that handles starts with AB. It's a Turing machine that accepts all strings that starts with AB over the input alphabet A, B. Okay, so we'll just write a simple Turing machine for that. So Q0 is a starting state. So whenever I see as A, replace it with X, keep moving right, go to Q1. Whenever I see a B, left, we say, and Q2 is an accepting state. Okay, and all the this symbols, state symbols are, I can write a, I can write a B, I can write a blank, and also I write a X. To denote that it has been visited, I write a X. Okay, all these are tape symbols. So this is my Turing machine. Let me take an input word ABA. So that word has to be accepted. So for this, I'll construct dominoes. I'm going to construct dominoes for this string ABA. Okay, so there are 7 steps in creation of dominoes. Okay, very simple steps that will help us create dominoes out of instantaneous descriptions. Okay, so we are going to create dominoes. Okay, creation of dominoes. I think we'll see that in a same slide so that it is easier for us to refer. Okay, step 1, what we'll do is we'll take our input string, we'll have it along with us and see, so that it's easier. So initially Q naught is in Q naught, see the transition diagram, Q naught. Okay, so Q naught sees this A means it writes an X and moves to right. So our Turing machine starts with the state Q naught. Okay, now the general thing for general domino for starting creation is, how do we represent the instantaneous description for this? Instantaneous description for this is Q naught comes and string ABA. Nothing to the left because nothing has been read yet, and the point Q naught is here and the read write pointer is here. The first character of the right string is where your read write head is currently positioned. Okay. So the general way to create a domino for this is create hash is a special character that we'll use. Okay, hash is a special character that we'll use to denote the starting and ending of the string in the dominoes. Okay, and you should have hash Q naught, the complete word, and a hash. So this is the general way to create the first domino. Okay, so this is the general one, and we'll create the domino for our problem, ABA solution. Okay, so hash we'll write. Hash, remember hash is a special character to denote the starting and the end. So we'll write Q naught, the word is ABA. So this is the first domino that we have created. Okay, so step 1, create a domino for the initial state and the whole string. So this is the always write the instantaneous description. So this is the instantaneous description. This is the ID, instantaneous description. So Q naught is the initial state and the pointer is to the always point. The read write head points to the first character in the right string. So it's an A. So for this we are writing a domino like this. So that is step 1. And step 2, we take all transitions with the right move. Okay. Step 3 will take the left move. Step 2 will take all transitions with right move. So we have one transition with right move. Okay. So what is the transition? Q naught, when it sees A, it replaces A with X and moves to right. Right. So our transition function will look like this. Q naught, when it sees A, it replaces it with, it goes to state Q1, replaces it with X and moves to right. Right. So this is the transition function. Now how to write our ID? We'll look at the tape. Let me say A, and I was at the state Q naught. Now A has been replaced by X. Okay, there is a B, there is a fine. It's a B and a. A has been replaced and with X, and I have moved to right, and the state is Q1. Am I right? And if I take the instantaneous description for this alone, for this A, it will be Q naught A X Q1. Let us not consider this B and A. Let us consider only the current string. Okay, and we'll write the transition. Q naught, on seeing A, replaces it with X and moves to Q1. Okay, so this is what I'll transfer it as a domino. Q naught, on seeing A, replaces it with X and moves to Q1. This we do for all right transitions. Don't write the entire string, just write for the current symbol that we are handling. Okay, with the entire string is still there, we'll write only for the current string that we are, current symbol that we are handling. So we are handling A, Q naught on seeing A. So Q naught on seeing A, replace it with X and move to Q1. Okay, so this we do for all right transition. And step 3, we take all for left move transitions. Okay, all left move transitions we have to handle in step 3. Okay, remember, first for initial state, step 1 is for initial state. Okay, step 2 is for all right move transitions. Step 3 is for all left. Step 3 is for all left move transitions. So left move transition will be a bit difficult. So here we have this Q1 to Q2 as a left move transition. So delta Q1 on seeing a B, what does it do? It rewrites it with X and moves to left with a state change of Q2. Okay? This means this is equal to Q2, Q2, comma, rewrite with X, comma, a left move. So this is our transition function. Now take this symbol alone. Please consider the current symbol alone and not the entire string. Okay, we are writing a generic domino. Okay, so let me take the current symbol that I am handling alone. So it is a B and I was in the state Q1. All right. So left I represent a Y. Y is any tape symbol. Okay, it's not a single tape symbol. Y could be any tape symbol. Okay, Y is any tape symbol to the left. I am at the state Q1 pointing to B. Left, I'm going to do a left move, and to the left of B there could be any tape symbol. Okay, so what I'm doing here is B is replaced with X in our transition, we know that, and I move to left to a state Q2 and it points to this Y. Okay, now if we write the transition, previously it was at Q1 Y and the pointer was at B, right? This is the ID, instantaneous description for this particular tape. Q1 is the current state, B, it was pointing to B, and the left side of B was Y. Now if you write the same sort of representation here, I'll have Q2, Y and X. I'm at the state Q2 and the head is pointing, the header, read-write header is pointing to Y and X. So if I'll write like this, and you know this is numerator, this is denominator in our domino. And one more thing is, in the place of Y, replace every tape symbol and write those many dominoes. That is very important. So you're going to replace. So generically, how we'll write is, we'll say Y Q1B by Q2Y X. So this is our domino. But in the place of Y, we are going to replace every possible tape symbol. So what are the tape symbols that we can write? Small a, small b, blank, and X. All these are the tape symbols that we can have. So you have to write all. A Q1B by Q2AX, comma B Q1B by Q2BX. Okay, I've replaced Y with A here. I've replaced Y with B here. Similarly, blank. Blank Q1B by Q2 blank X. Okay, these are separate dominoes. Okay, fine. The next domino is, I'll replace it with X. You can see we have 4 input tape symbols, A, B, blank, and a X. So instead of Y, I'll replace X. Y means any tape symbols. Q2 XX. So I've got, so this is the output for step 2. This is the output for step 3. Okay. Fine. So I've generated these many dominoes out of it. Okay. And step 4, after this it is very easy. So step 4, write for all tape symbols. All tape symbols we are going to write dominoes. Step 4 to 7, it's very easy. Just you'll have to write for all tape symbols like this. A by A, B by B, X by X, and blank by blank. This is step 4. And step 5, for all possible tape symbols along with the accepting state Q2. You can see the accepting state is Q2. For all tape symbols along with the accepting state Q2, we are going to write, for each tape symbol, we'll write 2 dominoes. Okay, how we are going to write is, we'll write A Q2 by Q2. We'll write Q2A by Q2. See, if you just follow how we create dominoes, then it is done. Okay, so for the single input symbol A, I've written 2 dominoes. What is Q2? Q2 is my accepting state. Okay, for every input symbol and for this accepting state combination, we are going to do this. Okay, so for every input symbol A, I write A Q2 by Q2. Similarly, I change the order, Q2 A by Q2. Okay, that is it. It's very, very simple. Just you're going to write it multiple times. That's it. So I'll repeat the same thing for B. P Q2 by Q2. Just change the position of B. That's it. This is for A, this is for B, then I'll do it for X and then for blank. So X Q2 by Q2, that is a domino, Q2 X by Q2. Similarly for blank, blank Q2 by Q2, Q2 blank by Q2. Okay. So these are the set of dominoes that I get in step 5. Only step 2 and 3 are a bit difficult. Others are all directly you're going to create dominoes. So what are we doing? We are trying to convert a Turing machine acceptance problem to a post correspondence problem. Again, step 6 also is very easy. Hard code directly. Nothing to think about. You just have to. Hash is a delimiting character. Remember, hash to be a delimiting character. There is a very big algorithm on these steps. So we'll not worry about that. Step 7, we'll create a domino like this. So step 4 to 7 are very simple. Direct hard-coded dominoes we are going to create. Just step 2 and 3 only we'll have to think a bit on based on right movement. Even right movement is straightforward. For the left movement alone, you'll have to remember to write it for every possible Y, you'll have to write the dominoes. Okay. So step 5 again, all possible symbols with accepting states. Write 2 arrangement for every tape symbol. Step 6 is simple and step 7 is also simple. Directly you're going to step 6 you're going to write with blank. Step 7 you're going to write with accepting state again. So these are the all dominoes that we have created. Now for the string ABA, you're going to check if you're able to get a post correspondence solution. Do you have a post correspondence solution? This is my question. I'm going to check if I'm able to create it. How will I do it? Just as we did it here. You are going to arrange dominoes. Arrange in any order, not a problem. Start with the initial state Q0, okay? And you're going to arrange. Initial state, we have created a domino, right? The first domino that we created, okay? You are going to remember that only. That's the only condition. You're going to start with this domino, okay? Start with this domino. We're going to create a post correspondence solution. So just start with this. Just keep arranging so that the numerator and denominator cancels out. Okay, using any of these dominoes created. Okay, so this is one domino. This is another. The next is set. This is the next set. Okay, so these are the dominoes available with. Consider them as building blocks. Okay, the real domino block. Okay, you're just going to make an arrangement so that the numerator and the denominator cancels out, and you're going to check if you're able to get a post correspondence arrangement that cancels out the whole numerator and the denominator. Just as we did it for this problem, we are going to arrange the blocks that we have just now created from this Turing machine acceptance. Okay, so as I told you, we'll have to start with the initial domino that we have created. Okay, with this domino hash Q0 ABA. Okay, so I will start with that. So this is hash by hash Q0 ABA. ABA is my input string. So this is the first domino. Okay, now I have a Q0 over here, right? So I'll choose something that has a Q0 in the numerator. Okay, okay, this because why should I not bother about hash? This hash and hash is cancelled. Am I right? This hash and this hash will be cancelled automatically. Okay, so now Q0 again is pending. So I choose a domino that starts with Q0. So I'll go and check. What is the domino that I have with Q0? I'll go and check. Only this domino and this is the other domino. I've just used this domino. So I'll try using the domino that I got in step 2. So step 2 domino I'll choose Q0 by, so step 2 domino is Q0 A by XQ1. Q0 A by XQ1. Okay, so this domino I'll choose. So if I choose this domino, what will I get? Q0 and A will be cancelled. So here also Q0 and A will be cancelled. Am I right? So what is the output that I have now after this arrangement? I have BA hash XQ1 in the denominator, BA hash XQ1 in the denominator. Am I right? So this was from step 2. Okay, this domino was what we created in step 2. If we go back and see the dominoes that we have created in step 4, it has individual for A, B, X, and blank. So I'll take 2 dominoes, B by B and A by A. Okay, so now this will help me to cancel out B, A, B, and A. Okay, now what will I get? I'll have only denominator that has hash X, Q1, B, and A. So this is what I have with me now, hash X, Q1, B, and A. Now again, I have in the step 6, I have hash by hash. So I'll choose that. Just choose something to cancel out. Okay, so I'll choose this. So hash and hash will be cancelled. Now I have a XQ1B. Now I'll go and check if I have XQ1B anywhere. Okay, you can see it here, right? XQ1B, you have it here. So I have a perfect domino that has 3 characters. So I can choose that. I'll choose XQ1B. What was the denominator? Q2XX. Okay, fine. Now what I'll do is XQ1B, the whole thing will be cancelled with the denominator. Now let me rewrite it again. What is the numerator? I don't have anything, as you can see. Denominator, start from this A. This whole thing is a denominator. A hash I have, Q2 I have, XX I have. Am I right? The whole thing I have. Now again I'll balance with A by A and a hash by hash. I know I have this dominoes with me. I'll arrange this. So individually I'll cancel A and hash. Individually I'll cancel A and hash. Okay. So let me rewrite it again. No numerator. I don't have a numerator. Everything is cancelled out. Denominator, I have Q2XX A hash. Q2XX A and a hash. Okay, Q2XX A and a hash I have. Now let me go and check if I have Q2X anywhere. Where do I don't have in step 1, 2, 3. Q2X domino, do I have anywhere? Yeah, in step 5, I created with all possible Q2 and input. So Q2X, I have it here, right? So I can choose this. Q2X by Q2, I can choose, right? So I'll choose that domino. Q2X by Q2, right? Q2X by Q2. So what happens? This will cancel. This will cancel. Right, now I have a XA hash. Okay, so and here I have Q2. So I'll separately do this. X by X, because all are tape symbols. A by A, I'll have hash by hash. So individually, the numerator, all these 3 will be cancelled, but my denominator, I'm building it. So my denominator now has Q2 XA hash. Am I right? My numerator doesn't have anything. My denominator has Q2 XA hash. Right? Now I should go and check. I know already I had a Q2X over here. Right? So I'll repeat it. I have a Q2X by Q2. That will help me cancel this. Okay. Now I have a hash Q2. Right? I have a hash Q2. So I'll repeat it with AA and a hash hash. Okay. So I'll cancel this A hash, A hash. Let me rewrite it again. Nothing in the numerator, but I have a Q2 A hash left out. Q2 A hash left out. Now let me go and find if I have a Q2A somewhere in the dominoes that I've created. I have this Q2A by Q2 I have. Okay. I'll just go and arrange that domino now. Q2A by Q2. This will be cancelled. This will be cancelled. Now what do I have? I have a hash Q2 with me. And I know very well that I have a hash hash. Okay. Now I only have a Q2 hash with me. The denominator. Q2 hash only I have with me. Okay. Now let me go to step 7, which is a halting where I have Q2 hash pattern. So this pattern I have Q2 hash hash by hash. I'll just arrange that domino over here. Q2 hash hash by hash. So these two will be cancelled with this. This individual hash will be cancelled. So my arrangement is valid. I have an arrangement and I have a post correspondence solution. So arrangement is possible. Post correspondence solution is possible. Okay, that means now where are we? That means a Turing machine acceptance problem can be reduced to, this is the conclusion, can be reduced to. We have taken an instance example, with an example you can prove. So we have taken a Turing machine that accepts any string that start with AB. We have taken a word ABA and we have proved that the Turing machine acceptance can be reduced to a post correspondence problem. So this is undecidable. Turing machine acceptance is undecidable. Therefore, PCP is also undecidable. So what have we done? We have proved that PCP is undecidable using reduction technique. This is using reduction techniques. From already known undecidable problem of Turing machine acceptance, from the Turing machine, we have constructed dominoes using the 7 steps. And then we tried arranging the dominoes, and we were able to cancel out the whole numerator and denominator, meaning that it has a post correspondence solution. So I'm able to reduce a Turing machine acceptance to a post correspondence problem. That means that if that is undecidable, this also becomes, it is undecidable. It is also undecidable. Okay. So this is the post correspondence problem.